We're in now 7.4, where we make the transition from exponentials to logarithms. If you're in Algebra 2, you've probably never seen a logarithm before. So let's get right into it. Take deep breaths. We're going to talk about what a logarithm is. We're going to talk about how to evaluate logarithms. We're going to look at doing them by hand or in your head without a calculator, and then we're going to talk about typing them into calculators. We're going to learn to simplify a particular structure of logarithms. They cancel with exponentials nicely, and that's what we're going to look at. And then we're going to talk about graphing. This is basically the summary, the introduction for logarithms. So let's get to it. Logarithm has a definition. So you need two positive numbers, b and x, and b can't be 1. The logarithm of x with base b is defined as follows. The log base b of x is y, if and only if b to the y equals x. So these are the same numbers being used here. If you don't recognize it, this structure is very similar to how we define division and subtraction. What this is saying is the logarithm is the inverse of exponential functions. These are going to undo each other. We read this over here as log base b of x. And the answer to a logarithm is always the exponent. It's the exponent you would stick on the base in order to get the number, the argument of the logarithm. So logarithm is a function. That's the first thing we note here. It has a domain and a range. That is an input value and an output value. So when you stick in a number from the domain, you get a number from the range. So here we've got x is the number you're sticking in. You can think of it as f of x. It's a function, is the answer that we're getting out. Since logarithm is an inverse, the answer that we're getting out would be part of the inverse function as well. And this is really how we think about logarithms. It's the way your brain can wrap around this, is by noting that this is basically the opposite of a separate problem. Log base 2 of 8 is y, if and only if 2 to the power of y equals 8. That's how the inverse here works. So we're looking for the exponent that you stick on 2 in order to get 8. And of course, 2 to the third power is 8, which means the answer to this logarithm is 3, because that's the power you stick on 2 to get 8. So logarithms, the easiest way for you to handle logarithms is to keep reminding yourself, until you just get used to it, logarithms ask the question, what power must I stick on this base, so the little number, b, in order to get this number, the big number, x. So in this case, what power do I have to stick on 2 to get 8? The answer, of course, is 3. Let's evaluate a few of these just to make sure you get the picture. So this is another one with base 2. This says log base 2 of 32. So what power do you stick on 2 to get 32? And if you do it in your brain, 2, then 2 times 2 is 4, and 2 times 2 times 2 is 8. You multiply by 2 again, you get 16. That's 4 times. You multiply a fifth 2, and you get 32. So you had to multiply 2 5 times. So 2 to the fifth power is 32, which means the answer here is 5. Please don't write on your tests or quizzes 2 to the fifth or 32. The answer is 5, because that's the exponent. The answer to a logarithm is an exponent. Log base 10 of 1. What power do you stick on 10 to get 1? Well, anything to the 0 power is 1. So anytime you have a logarithm and there's a 1 for the argument, the answer is 0, because anything to the 0 power is 1. Log base 9 of 9. What power do you stick on 9 to get 9? Don't overthink it. You stick a 1 on 9 to get 9. 9 to the first power is 9. Now this one a bit trickier. Notice we've got a fraction here. So 25 is related to 5 because it's 5 squared. But it was a fraction, the base. So we need to flip it upside down. And as I keep trying to get into your brains, negative exponents are what take reciprocals of numbers. Negative exponents do reciprocals. So this is going to be negative. Now the negative is going to flip it upside down to make it a 5. And then we need to square it to get 25. So the answer here is negative 2. The negative turns the 1/5 into 5, and the 2 turns the 5 into 25. So 1/5 to the negative second power is what becomes 25, and that's why it's the answer here. Anytime these are in reciprocals of each other, you're going to end up with a negative from your logarithm. Let's practice a few more. So I have here log base 3 of 81, log base 1/4 of 256, log base 10 of, let's see, that's 1,000th, and then log base 64 of 2. So pause the video real quick, try these, and then I'll review the answers now. All right, here are the answers. So let's talk through them. Log base 3 of 81 says what power do I stick on 3 to get 81? And 3 to the 4th power is 81. 3 times 3 times 3 times 3. So the answer is 4. Now this one right here, 4, it turns out 4 times 4 is 16, times 4 is 64, times 4 again is 256. So the 4 times, but because it's 1/4, we need the reciprocal, so we have -4. Conversely, log base 10, if we multiply 10 3 times, we get 1,000. But what we want is 1,000th, so we have to do the reciprocal, and that's why it's -3. And this one is even weirder, because the power you stick on 64 to get 2, the problem is that 2 is the 6th root of 64. So what we need is the 1/6 power, which is the same as the 6th root. So when the argument is smaller, you're going to get a number less than 1 out here. Evaluating logarithms on a calculator, most of the time, and actually in lesson 7.4 in our books, you're going to be assuming that if you're doing a logarithm on a calculator, it's either a common log, which has base 10, or a natural log, which is base e. Now the common log, we don't actually write the little 10. So if you're doing base 10, you just write the word log, and we all remember that log, there's no base, is base 10. So for example, log of 10 is 1, because 10 to the first power is 10. Log of 100 is 2, because 10 squared. Log of 15, you're going to need a calculator for. It doesn't go nicely. So you should be able to find a log button on your calculator. On a TI-84, it's on the left side right next to the 7. It just says log, L-O-G. You push it, put the 15 in there, and it'll give you 1.176. The natural log uses base e. We talked about e a little while ago. It's around 2.7. But this, you have ln. Now this is a lowercase l. It's how we write it when we're writing them. I think on the most calculators, they're using capital letters. You'll see a capital L and an N. It stands for logarithm and natural. I think it was French that they're backwards. But ln. So the ln of e is 1, because e to the first power is e. The ln of 1 is 0. Anything to the 0 power is 1. If you're doing one that you don't know, like ln of 15, stick it in a calculator. Push the ln button, put in the 15, push enter. 2.08 is the ln of 15. When you're doing logarithms that don't have a base of 10 or e, you have to use a trick. TI-84 graphing calculator has a function called log base, and you can find it in the math menu near the bottom. There's a math button. It's on the left side. If you push the math button, scroll to the bottom. If you've got a newer calculator, it'll have a function called log base, and you can do it on your calculator. If you don't have access to a graphing calculator, like the calculator on my phone doesn't have it, so sorry about that. My daughter interrupted the video. I think I paused it successfully. So we'll get back to this. If you're using your phone or like a scientific calculator that doesn't have a way to put in a base, you can actually use a trick, and that is you can divide two different logarithms to make this logarithm. So for log base 3 of 12, you do the log of 12, you do the log of the argument, divided by the log of the base, log 3. And you get the same answer you would get from log base 3 of 12. Another example, log base 9 of 5. Here the 5 is smaller, so we're expecting a number less than 1. You do log of 5 divided by log of 9, and that'll give you the correct answer. So you can do it on a calculator whether it has log base or not. So next, simplifying logarithms. I already mentioned logarithms and exponentials are inverses. They undo each other. So when you have a situation where you have an exponent, an exponential expression, and a logarithmic expression, and they have the same base. So here you've got e, and then ln has base e. They're going to cancel each other out. So e to the ln of 9, the e to the, and the ln of are going to cancel, leaving just 9. Similarly, 5 to the log base 5 of x, the 5 and the log are going to cancel, because here we have an exponential with base 5 and a logarithm with base 5. It's going to leave us with just x. The opposite, or backwards one of that, if you have a logarithm with an exponential inside it, and they have the same base, so log base 5 of 5 to the x, the log and the exponential are going to cancel, leaving just, in this case, x again. This last example here you'll notice it's a logarithm with an exponential inside, but the bases don't match. So one of the things we have to do is rewrite sometimes the argument so that it is a power that matches the base. We need to rewrite 27 as a power of 3. Turns out 27 is 3 to the third power. So we can rewrite this as log base 3 of 3 to the 3x. The log base 3 and the 3 base cancel, leaving 3x. So that's simplifying logarithms, which is something that you'll be expected to do. And lastly, graphs of logarithms. You've been graphing exponentials. Graphs of logarithms are very similar to exponentials because they're inverses. Remember when we did inverses in previously in this year, we learned what you do for inverses is you switch the x and the y, and that creates a new function. So we're going to do the same thing here. We're going to switch the x and the y, which switches the domain and the range. So when we look at a logarithmic graph, the exponential function had an asymptote at y equals 0, horizontal asymptote, y equals 0. When we switch all of our x's and y's, we're going to switch to a vertical asymptote, and the y is going to become an x, so it's x equals 0, which is going to give us a vertical line, an asymptote, instead of a horizontal one. The old, for exponential functions, domain was all real numbers, and the range was always y is greater than or less than wherever our asymptote was, in this case 0. We're going to switch those as well. So for a logarithm, the domain is going to be x is greater than the asymptote, and the range is going to be all real numbers. So taking a look at the pictures, here's our exponential function. This one is y equals 2 to the x. You can see it goes through 0, 1, and it also goes through 2, 1, 2, and it goes through 2, 4. This is our basic 2 to the x exponential function. The y equals log base 2 of x function is the inverse. It has a very similar shape, but it's kind of on its side. Here we have a vertical asymptote. See the line it's approaching but never touching right here. That's at x equals 0. It's vertical instead. And the graph's going to veer off to the right instead of veering up. Every point on this graph corresponds to a point on the other. So 0, 1, if we switch the x and the y here, we get 1, 0, which is this point right here, 1, 0. 1, 2 is 2, 1 on the other graph. And 2, 4 we can write as 4, 2 on the other graph. So this graph is going to veer off to the right instead of going up, and it has a vertical asymptote instead of a horizontal asymptote. And that's logarithms. That summary, I'm not sure, is really sufficient, so I'm actually going to switch and show you how to actually graph a couple by hand, just to make sure you get the picture. So I'm going to start with y equals log base 3 of x. So the first thing I'm going to note is I need a vertical asymptote. Now the vertical asymptote for a logarithm is going to happen where the argument, the inside, would be 0. So if there's nothing being added or subtracted inside your logarithm, your vertical asymptote is going to be at 0 for the first one. Note for our second graph, we're going to have a subtraction in there. It's going to move the vertical asymptote. For exponential functions, you look for the number outside because the asymptote moved up or down. For logarithms, you're going to look on the inside because the asymptote moves left or right. In this case, it's at x equals 0. Now I need a few points. Now, even more so than with the exponential functions, it's important that you pick your x's strategically unless you want to type every single point into a calculator, which, if you're using a calculator anyway, is a reasonable strategy, but not particularly helpful since if you have a calculator, you could probably just graph the function on the calculator. We're trying to get a feel for how these work. The easiest point to stick in is always going to be make the inside 1, because, as discussed, anything to the 0 power is 1. So anytime I say, what power do I stick on 3 to get 1, the answer is 0, because anything to the 0 power is 1. So if my argument is 1, the answer is 0, 1, 0. The next nice point to stick in is the one that makes the argument equal the base. So I want to stick in 3, because 3 to the first power equals 3. So what power do I stick on 3 to get 3? 1. Then the next power of 3 is 9. I should say the next nice power of 3 is 9, which is 3 squared. So what power do I stick on 3 to get 9? 2. I may not be able to fit that on my graph, but I've got 1, 0. I have 3, 1. 4, 5, 6, 7, 8, 9. Yeah, right there, which is kind of ironic. So this graph's going to come up through these 3 points. I probably won't draw it that far. So up from the asymptote through my points, levels off as quickly as exponential functions grow. So this is log base 3 of x. Its domain, there's no graph at all to the left. All of the x's on my graph are bigger than the vertical asymptote. So x is greater than 0 is my domain. For the range, I'm looking for y's, and notice this arrow goes all the way down to negative infinity. This graph will keep going up. It gets very shallow and has to go over really far to make any real distance up. But it's going to keep going all the way to infinity. So the range is all real numbers. It goes all the way up and all the way down. And if you remember, for exponential functions, these are just reversed for logarithms. Let's take a look at the slightly more complicated graph. Log base 4, x minus 2 plus 3. As far as order of operations, you have to do what's in the parentheses first. Then we're going to need to evaluate the logarithm before we add 3. So, first thing I'm going to do is find my vertical asymptote. I need to figure out what makes the inside 0. In this case 2, because 2 minus 2 is 0. If you have trouble with that logic, just take whatever's on the inside and make a little equation where it's equal to 0. That you should be able to solve. Add 2 to both sides. X equals 2. That's going to be where my vertical asymptote is. Here at x equals 2. Remember, it's vertical, not horizontal. Then I need a few points. So what I really want to do here is make the inside equal to 1. So that means I need to stick in 3, because 3 minus 2 is 1. That gives me log base 4 of 1 plus 3. What power do I stick on 4 to get 1? Well, 0, because anything to the 0 power is 1. So that's 0 plus 3, which is 3. The next one I want is to make the inside equal to my base. I want the inside to be 4, so I need to stick in 6, because 6 minus 2 is 4. That'll make these the same, and I'll get log base 4 of 4 plus 3. What power do I stick on 4 to get 4? Well, 1. Right? 4 to the first power is 4. 1 plus 3 is 4. Now, when you're doing this, if you follow these through, let's see, the next one should be 16. So I need to stick in 18, because 4 squared is 18. Or 16, sorry. So log base 4 of 16. So that'll be 2 plus 3 is 5. My y's are going 1 up each time when I make the argument on the next power of 4. The next one, I would need to make the inside 64, which is the third power of 4, and I'd get 6 right here, because 3 plus 3 is 6. This is already going to be off my graph, though, so I'm going to graph 3, 3. And I'm going to graph 6, 4, 5, 6, 1, 2, 3, 4, 6, 4. As you can see, it's already getting pretty shallow there. It's veering off to the right. I am not going to fit 18 on there. I could put 1 on the left. Some of you aren't going to like it, but I really need to make the inside equal, say, 1/4 to get a nice answer here. So if I need the inside to be 1/4, x minus 2 equals 1/4, then x is going to have to be 2 1/4, or 9/4 if you prefer. So in this case then, I need x is 9/4, which makes this log base 4 of 1/4 plus 3. What power do you stick on 4 to get 1/4? Negative 1. Negative 1 plus 3 is 2. So 9/4, which is 2 1/4, has the answer 2 right there. So we're coming up from the asymptote, and we go through our points. Make sure you're nice and shallow, because the next point would be over here at like 18.5. It's pretty far over there. And there are both of our graphs. This should be enough to get you started, so good luck on your work.